Okay, today our topic is about combinational case studies. So this is a design procedure. So the first one, you have to specify the what you need of the circuit. The second one is formulation, optimization, design entry, transition mapping, and verification. So okay, this is the first one, BCD adder. Okay, so the problem with BCD is when you have 6 plus 3 you get 9. So BCD will display 1001 to represent 9. So let's say you have to add certain numbers which is more than 9. For example, here is 5 plus 7. 5 plus 7, 5 is 0101. You add 70111, you get 1100. This is not correct in the BCD terms, because in the normal binary it represents 12. So what we need to do is, in order to make sure the output, correct output is display 1 2, so you have to do adjustment, which is you have to add with 6, 0110. Okay, for example, you have 5 plus 7, you get 12. So later you add another 6, which is 0110. So your answer will be 01001. So 0010 represent 2, 1 represent 1. So the correct BCD will display 1 2, because remember that the BCD only start from decimal 0 until 9. So 0 binary base, normal binary, decimal 0 equal to 000, decimal 1 equal to 001 in BCD, and so on. When you have 1001, it represents 9 in BCD. Okay, if you have decimal 10, it cannot display in BCD terms. The second example, let's say you have 8 plus 7, you get 15. This is a non-BCD, so you have to adjust with adding by 6, which is 0110. Your answer will be 1010. When you represent in BCD, the fourth bit from the left is equal to 5, another one equal to 1. So the answer will be display BCD in 15. So another example is you have 9 plus 9, which is 18. So 18 in non-BCD is 10010. So you have to add another 6, 0110, you get 1100, so equal to 18. This figure shows a BCD binary adder that add two BCD digits in parallel and always produce a valid BCD sum and carry out bit. The basic component of the BCD adder is a regular 4-bit parallel adder plus additional circuits to perform adjustment when necessary. This is additional circuit to make sure your addition using BCD is correct. Notice that at this part you have to add which is 6 in this part, the last part, in order to get the correct BCD. This table shows the all possible adder output. So this is your decimal 0 until 19 for this example. You have binary sum C, S3, S2, S1, S0, and you have another column to show that BCD sum, represented by K, Z3, Z2, Z1, and Z0. The first decimal 0, if you notice, when we add, we get the binary sum, normal binary, we add each other, you get the sum. So if 0 represented by C0, S3 0, S2 0, S1 0, and also S0 0. When you are using the BCD sum, so K always 0, Z3 0, Z2 0, Z1 and Z0 also 0. Okay, look at the decimal 9. Decimal 9, when you get the binary sum, your C is still 0, your S3 become 1, S2 0, S1 0, S0 1. In other one, BCD sum, your K is 0, your Z3 is 1, Z2 and Z1 is 0, the last one Z0 is 1. So it's like equal when you compare binary sum to the BCD sum. When 0 to 9, for example, when 5, this column binary sum, you get 5. Another binary BCD, another column for BCD sum also 5. Okay, now look at the numbers decimal which is more than 9, which is 10. When you get binary sum, normal binary, you do addition, you get binary sum. The answer is C0, S3 is 1, S2 is 0, S1 is 0, S1 is 1, S0 is 0, which is equal to 10, right? But when you do, in order to represent BCD sum, 1 0, so this is represent the 4 bit, the first 4 bit from the LSB show 0, and another K which is 1 represent 1. So this is 1, this is 0. Okay, how you get this? Actually, you have to add 1 0 1 0 binary sum, normal binary sum with 6, right? With 6, so which is 0 1 1 0, so you get this 1 0 0 0, and then when you present in BCD, you get this 1, this is 0. Okay, look at another example. For example, we go here, 5 plus 7, you get 12, right? So how to get correct 12? You must add 6 in order to get 1 0 0 1 0. So refer back to this table which is show the 12 for the BCD sum. So your last answer is this is 1. Another 4 bit represent 2. So this is a 1, this is a 2, represent 1 2. How you get this? By add 6 from with binary sum. Okay, this one. Right, this one shows these rows. How you get this BCD sum. And we go for here, which is a 15. This is a non-BCD. We are going to get the correct BCD. You have to add 6. The first one you get binary sum, you get 1 1 1. So you go to 15. This is 15. You get 1 1 1 1. How? When you obtain BCD sum, the bit change become like this 1 0 1 0 1. So by having add 6, so you add 15 with 6, 15 with 6, you get this. So the 4 bit from the LSB display 5. This is a 5. The other one is 1. So 1 5. Okay, looks at this K-map. So actually this K-map, when the sum axis 9, which is when your summation axis 9, which is from 10 above, right? Your carry bit C is 1. So your carry bit is 1, which is a K is 1, and then the binary sum is between 10 10 and 11 11. So when we derive the K map, so inside the cell is represent the K. So when the 0 0 1 1, for example, the first cell here 0 0 1 1, K is 1. So where is 0 0 1 1, K equal to 1. And when you fill up everything, so K equal to 1 2 3 6 until this one, so you fill in this, you get the equations. K equal to C plus S3 S2 and also S3 S1. Okay, you get this equation. If C or F is true, add with this one, this looping, and also add this one, this looping, so you get K. So by this equation, we add this one, K equal to C, or with S3 and S1. Another OR is combination of another AND gate, which is S2 and S3. So you get K here. K here equal to 1 connected to these correlation factors, which is, if you notice, the one here connect to the third bit and second bit. The first bit is 0 and the fourth bit is 0. So this is actually represents 6. Whatever you get summation, binary summation, you must add with 6 here in order to get binary BCD.